typical question I may ask during exam is that why do we have, say, electron accelerators with energies 100 GeVs? Well, this is almost maximal energy we have, while for protons we have accelerators up to 7 TeVs. And so you need to understand why it happens so. In the future we are planning to have some linear accelerator, maybe at the energy 500 GeVs, which is still, say, 10, 20 times smaller than the highest proton accelerator. So why it happens so? Can you give me the answer now? Why it is difficult to create high energy electron accelerator? Why it's easy to create say, proton accelerator of the very high energies? Any answer?
Maybe for the energy loss?
Yes, this is what we have studied in the end of last lecture. This is because of synchrotron energy loss. And this is not a joke, really. This is a big problem, you know, which actually costs billions and billions. And for your generation, if you eventually decide to create a very high, more high energy than LHC, then that will be a big issue. So let me give you some very simple arguments why this synchrotron radiation is so dangerous, why it has so strong dependence on the momentum of the accelerated particle. Let me give so-called classical, I think it's switched. Classical picture. And the point is that in contrast to usual radiations in electric field, here we deal with magnetic field. And in this case, the force which acts on the particle is proportional to the speed or velocity of the particle. Remember, in the case of usual radiation, the force was just charge multiplied by, this is strength of the field. This is not the energy, but strength of the electric field. Here, we have this, the force which is proportional to velocity and therefore to momentum over the mass of the particle. So, and this is the origin of the dependence which we have already written last lecture. So let me give you a very brief derivation of what's going on. So we have circular orbit, and suppose in an initial moment, in some moment, the particle moved along this direction. In the next moment, say in the unit of time, after say 1 second, it turned and the momentum is in this direction, like prime. Now the force, you probably remember this from classical physics, classical mechanics, is the ratio of change of the momentum in the unit of time. So force can be expressed as a change of momentum in unit of time. Okay, so let's take unit of time. Suppose first particle was here, and then after unit of time it is here. The distance particle passed is just given by velocity, right? So velocity is the distance in the unit of time. So that this distance from the first point to the second one is v. And therefore, the angle, this one, is given by velocity over the radius, approximately, right? So this is the radius of orbit, and this is the distance which particle passes in unit of time. Now, delta p, again over dt's in the unit of time, then will be given by momentum itself multiplied by this angle. Because this angle is the same as this angle. This is orthogonal to this, and that one to that one, and therefore this is also alpha angle. And therefore, the change of the momentum in the unit of time is given by momentum and alpha, and that will be equal to, so p v over radius, and velocity is p over the mass, and so we will get p squared over the mass of the particle over the radius. You see, it is this very strong dependence of the force and the momentum which led to so strong dependence of energy loss on the momentum of the particle. Now, the energy loss, remember we already did this for usual radiation in the electric field, is when we go from, it is proportional to essentially acceleration square, and this square is because we are going from classical to quantum case. And now what is the acceleration? Acceleration is the force over the mass of the particle, and therefore we take this expression, p squared, mx squared, the radius. And when we square this, we will get our formula, which I have reproduced last lecture, p to the fourth, mx to the fourth, and radius squared. And of course we need to add electric charge of the particle, and there are some coefficients. So we essentially derive this formula. Of course, exact derivation also contains some other parameters like emittance, but dependence on the most important parameters can be actually derived in this way. Questions? Okay.
One question.
Yeah.
Why did we say, can you repeat that always, why did we say that the dependence of the energy loss is proportional to the acceleration square, please?
Oh, so, look, this is empirical expression. Let me put this. Remember, we did the same in the case of an electric field. So, in classical, it's acceleration. In classical case, so the energy loss is proportional to acceleration. When we go to quantum case, so this is kind of empirical relation. When we go to quantum case, we square this. Good. So let me give you some information about accelerators and properties of the accelerators, or characteristics. First of all, we can classify accelerators by the type of the particles we are accelerating, and we have E plus and minus colliders. So we will discuss experiments and the results obtained by these colliders. So the examples are LHC, for instance, and also SLAC. It's kind of in stoichiometry, we have a plus and minus collisions. Then we have accelerator when we collide electrons and protons. So that was in DESI, Germany accelerator. So here we have LHC examples and SLAC. Then we have proton, anti-proton colliders, and that was Tevatron, one of the latest examples. Tevatron in Fermilab. LHC is proton-proton collider. Here is proton-antiproton, and this is LHC. It's so here is not LHC, sorry, this is LEP. This is the same ring, LEP. LEP and LHC use the same ring near Geneva, and here we have what I have discussed, acceleration with maximal energy in the center of mass, 200 GeVs, and here we have already certain TeVs because this is proton-proton collider. And also we have a number of experiments when we have neutrino interactions with nuclei, and this is T2K and the nova acting accelerators at present. Now, further classification is what is configuration of the experiment. And there are two configurations. One is fixed target. When we have accelerator beam which hits the target, which is staying as kind of piece of material, and then colliders. So here we have target, which is at rest, and then accelerated particle hits the target, and then we see what is produced here. Here we have acceleration of both colliding particles, and so we have some secondary particles and observe them. Crucial characteristic of the accelerators is total energy in the center of mass. And centrum of mass system. So what is this? You can introduce invariant S, which is P1 plus P2, and these are four momenta of colliding particles. Also here you have colliding of particles and particles with particles, but one is at rest. So this is Lorentz invariant, and we can write this as E1 plus E2 square minus P1 plus P2 square, right? Now, let us consider the system of coordinates where P1 plus P2 is 0, and this is precisely the centrum of mass system. In this case, S, let me write already square root of S, is just E1 plus E2. So this is Lorentz invariant. You can introduce it in any system, but the physical meaning of this square root of S, this is total energy in the centrum of mass. Okay? And suppose you want to produce some new particle. Then the most economical way is, and you can consider again this in the centrum of mass system, when you have collisions of two particles and produce new particle at rest with some mass mx. Because if this particle is moving, then you need to have more energy, or if you produce some more particles, right? So the minimal situation, the minimal energy to produce a given particle x with mass mx is when you have E1 plus E2 equals mx. Again, if you produce some new particles, two particles or more, then you need to have more energy. So what is important that square root of S gives you what should be the minimal energy to create a given particle with the mass mx. So if you have particle of say 100 GeV mass and you collide particles with energy, say 20 and 30 GeVs. Of course, you are not able to produce this one. And therefore, to have a possibility to produce new particles, you need to have more and more energy in the center of mass. It is this one, not in the laboratory frame. Because one particle is staying, another is moving, and you need to estimate, to find what is this square root of s. Okay? So that you will have n exercises for this, and I don't want to proceed further. So square root of s, or total energy in the center of mass, gives you the idea what is energy available for you. So, for instance, you have E plus, E minus. It can go to some new particle, for instance, Higgs. Or better, let me put Z0. So this is the boson which is responsible for the weak interactions we will discuss later. Actually, this is what has been studied at lab. And to create Z0, you need to have the total energy in the centrum of mass of E plus E minus, which is equal or bigger than the mass of Z boson. Another very important characteristic, and when you go to this accelerator business, you always hear this, luminosity. The key point that even if you have enough energy, it is not enough to absorb some new particles. It is not enough because what is important also how many events you will see. So it may happen that the cross-section is so small that during your time of observation, the probability to create your particle is 10 to the minus 5, for instance. You are working 10 years and the probability is, say, 10 to the minus 5. And therefore, nobody will give you money to do this research. You need to have probability bigger than 1. You need to have many events. The more, the better, of course. Then you can study, to perform detailed study. So this is crucial parameter of accelerators, which is luminosity. And let me discuss a little bit this and derive the formula, and you will have an exercise to compute luminosity. So, important characteristic is rate of events. Number of events of a given type in a unit of time. So, clearly that this rate is proportional to cross-section. This is cross-section. And then we add here characteristic of your accelerator. So, cross-section is characteristic of interaction of single particle with single particle. Then we just add parameter such that allows you to compute the rate of events once you know cross-section. So if you know cross-section, then you can compute the number of events if you know also luminosity. So this is why this parameter is very important. Now, what is dimension? So this is luminosity. And this is number of events of a given type in unit of time. So, the dimension of luminosity is therefore 1 over centimeter square second. So let me show you how we compute luminosity for colliders, for instance for LHC, and we will have an exercise. In the case of synchrotrons, we collide bunches of particles, so we accelerate particles in bunches and then eventually collide these particles in bunches. So typical configuration is the following. You have some interaction region in which accelerated beams are crossing and therefore interact. So let me put, this is one trajectory. Of course I exaggerate, this is another one. And you have bunches of particles, because acceleration is not gives you continuous flux, but it gives you bunches of particles. And this is another. So you have two pipes in which particles are moving. This is one pipe. This is another pipe. And in some area they are intersecting. Well, at LHC, for instance, you have two pipes in the same circle where you accelerate protons in one direction and in another direction. And then at some points these pipes merge and the particles are colliding. So suppose this is beam 1, and suppose we have, let me see notations what I used, N1 number of particles in each of these bunches. It can be 10 to the 11, big number of particles. And the number of these bunches is N1. So you have the ring and there's N1 small number of bunches. I think it's something like 2,000 bunches are moving in LHC. The same we are introducing for the second beam. We have N2 and N2, and in fact it can be symmetric. So the number of N1 and N2 are the same, and then small 1 and small 2 are the same. But in principle it can be different, especially if you have acceleration of different type of the particles. Then the important thing is the size. So each of these bunches looks like this, and LHC is the 7.5 centimeters length, and it's very small diameter. And what is important is area, and the area is 4 pi sigma x and sigma y. This is not a cross section, but this is, if you look at your bunch from this side, then this is sigma x and the sigma y, and this is z direction. Finally, important parameter is the number of times each bunch rotates in your pipe. So it happens that you may have, say, 7 orders of 10 to the 7, 10 millions per second. Every bunch is doing circle. So you have 10 to the 7 number of rotations inside the bunch, inside your circle. Okay? So that's a frequency of rotation. So take a given bunch, and in 1 second it has 10 millionths time crossing this collision area. So you need to take into account this, of course, right? Once computing number of events. So another important parameter is L. This is the area of crossing of the beams and circumference of your accelerator or the pipe. So in LHC this is 27 kilometers. So this is the length, total length of your circle. Okay, so that's what we need to derive expression for the rate of events and for luminosity. What I will do, I will use expression which we already have derived for the rate of events when we had a fixed target situation, when we had, remember, neutrino beam, which is entering the detector and has a collisions. So we have derived the following formula. The rate was the flux of events multiplied by the number of events in the target and multiplied by cross-section. So this is what we have derived in one of the first lectures. Good. So what we will do is the following. We consider one of these beams, one of the sets of these bunches as a flux and another as a target. Okay? So let's see what does it mean. So that we will consider as a target. Target. And this is a beam. Then the derivation goes like this. Number of particles in the target is given by, of course, number of bunches so n1 is, so let me just to avoid confusion, so that's multiplied by n detector so I just let me not to confuse because I switched from one notation to another one. So that's is number of what I have introduced n1 and n2, what is n small and what is n big, because eventually they will enter symmetrically. So this is number of bunches and this is number of particles in each bunch. So let me put here n2. This is number of particles in each of the bunch multiplied by the number of bunches which are in intersection region. So that is given by n2, total number of bunches, multiplied by L over C. Okay. So this is number of bunches, total number, which are moving in the pipe 2, but the number of bunches within the collision region is the ratio of the size of this region over the total circumference. Okay? So then that will be N2, L over C. Now let us compute the flux of particles 1. And the flux will be given again by the number of particles in a given bunch multiplied by the number of bunches multiplied by frequency and divided by the area. That gives us the density of flux of particles of the first type. So this is total number of particles multiplied by frequency because they are appearing many times, and we need to divide, this is total flux, and then we need to divide over the area, right? Because we want to know the flux in the unit of area, and that's why we divide by A, which is given by that expression. Now the luminosity, so let me put it here. Then the rate of events, so luminosity, from this formula, this is the luminosity. Luminosity will be given by the product of this flux, which is N1, N small 1, divided by area, multiplied by F, and then we need to multiply by N2, which is given here, which is N2 multiplied by N1, N2 small, and then we need to have this L over C. So this is expression. And you see it is symmetric with respect to 1 and 2. So we have N1 small here, N2 small here, we have N big 1 and N2, then frequency of rotation over the area, and then L is the size of the intersection region, and then C, the length of your pipe. So this is expression for luminosity. Questions? And the formula is more or less clear, that the physics is transparent. Of course, the bigger number of N1 big, N1 small, N2 small, N2 big, the bigger the frequency, the bigger is the luminosity, right? And here is A is the area, because the denser you make it, the more collisions you will have. Apart from luminosity, so we also introduced integral luminosity. When we simply integrate over time, L what we have derived. So it may happen, and usually in the experiment you have luminosity which changes with time. You may have some just empty days, then things are changing. So when you do this integration over total exposure time, then you will get integral luminosity. So the integral luminosity using this gives you immediately the number of events detected is not a rate, but number of events multiplied by cross-section. So this is total number of events, let me put here total, which you will observe during the time of your experiment. So this is dimensionless, and therefore integral luminosity can be measured in the units of 1 over sigma, cross-section. So it's clear, if your luminosity just equals 1 over sigma, then you expect to observe just one event. So if L integral equals, not dimension, but just quantity, sigma, this means that you expect total number of events 1. Unclear according to this formula. Now we measure cross-section in the units which we call bardens. Which is 10 to the minus 24 centimeters square. This is typical cross-section for strong interaction processes. Also some electromagnetic processes have so big cross-section. Other units we are using are millibarn, which is 10 to the minus 27 in the same units. Then picobar, which is 10 to the minus 36, and femtobar. Let me put this here, femtobar, which is 10 to the minus 39 centimeters squared. And this is very common. You can listen that we have cross section, say 1 femtobar. And then according to this formula, we can measure the total luminosity in inverse units of femtobars. And you can listen very often that we have collected luminosity, which is say 10 femtobars. For instance, LHC collected in the last year of operation, now it doesn't work, so it's now there's updating phase. And they have collected, for instance, L integral, which is 130 femtobar minus 1. Which means that if you have cross-section, which is 1 femtobar, then with this luminosity you are expect in average to observe 130 events. And finally, I want to give you some characteristics of acting accelerators. Let large electron-positron collider, it's E plus E minus machine. The length of the pipe, circumference, see, so this type, and this is accelerator, is 26.6 kilometers. Well, let me put here in kilometers. The energy in GeV is 110. And finally, luminosity in the units centimeter minus 2 second minus 1 was 5 10 to the 31. That accelerator was working during 90s, at the beginning of this century. Then Tevatron, which is proton-antiproton, which has the length of the ring 6.3 kilometers. The energy was TeV, 10 to the 3 GeVs, and the luminosity was 2 10 to the 32. And finally, LHC. LHC is proton-proton machine. It has the same ring as here, with the length 26.6 kilometers. Now the energy of each beam is 6.5 TeVs, but it will be 7 10 to the 3. Each of the protons will have this energy. And the luminosity is the peak luminosity, because it changed with time, was 10 to the 34 in these units. Now tell me, why this luminosity of LHC is much bigger than luminosity of Tevatron and LED? Who can answer? See, it's almost 3 orders of magnitude, and here is 2 orders of magnitude bigger luminosity. So why? the luminosity of LHC is much higher than the luminosity of other machines, other colliders. Any idea?
Event number.
Say again.
Event number.
No. So this is luminosity. Event number when you multiply luminosity onto cross-section. This is number of events you are expected to observe. Luminosity is characteristic of accelerator and configuration and collision area. So this is what you should know from your accelerator guys. So you want to compute the number of events. You are a theoretician and you are doing computation of cross-section. And then those guys from accelerator physics should tell you what is the luminosity, and then you compute for them what is the number of events of a given type you are expecting. So this is characteristic of accelerators. My question is, why we have here so big luminosity in comparison with this one and that one?
Synchrotron radiation?
Well, that actually affects more like an energy of acceleration. Of course, you see here is 110, and here is 70 times bigger or 60 times bigger. So that is determined by radiation, but not this one. Sorry? No, there's no still collisions. It's just a property or characteristic of fluxes you are producing of these colliding particles. You can look back at the form. Yeah?
We get one that's high fiber circuit and the other one that's AC. So that may contribute to the higher luminosity.
I don't know why it is so, it's difficult to hear. I'm sorry. So again, say.
Can you hear me now?
Yeah, better now.
Okay. So I'm saying is, so we have two pipes that one is as a circuit and the other one acts as a beam. So because they're like proton, so maybe the luminosity is higher.
Other options?
I guess the region where the two beams collide, the length is larger for the LHC.
Well, but this is not 2 orders of magnitude. They are different, but of the same order, as you can imagine. So, not this, especially, this is not the reason, main reason.
Okay, then it's a frequency.
And also this is, frequencies are different, but even this is not the main reason.
What's colliding?
True, so but what precisely is important? You see, here you have protons and protons, and you have a lot of protons around. You take water, you have hydrogen, right? So, but here you have antiprotons. There's no antiprotons around us. I mean, you need to create these antiprotons. And this is the big problem. Like there, you need still to create positrons and then accelerate them. Of course, you have some particles from cosmic rays, but the number is very small, the flux is very small. So, the main reason is because you need to create antiprotons first, which is non-trivial. You see the procedures, you first create antiprotons. Then you cool down them and then accelerate. And therefore, of course, the flux and the number of antiprotons is much smaller than the number of protons. It's not symmetric situation as I have described. So this N1 and N2 in such a situation are very different. It's very different. Because it's different, you need to create these antiprotons and also positrons. And actually it was a big discussion when people in the early days discussed what should be LHC, proton-proton or proton-antiproton. And eventually because proton-antiproton is very nice in the sense that you have annihilation process, and therefore it's easy to create something new out of this, a particle-antiparticle or quark-antiquark. Here you have mostly, here you have proton and proton. So, and it was a big discussion, what should be type of the accelerator? And eventually people stop at this, preferring to have bigger luminosity. Also the number of, say, quarks and antiquarks in this system is much, much smaller. Antiquarks, number of antiquarks. Okay. Now we will switch to discovery of the second neutrino, which is very important discovery. You will see how many physical consequences come out of this. Again, let me repeat. Of course, I'm not discussing all discoveries in particle physics. I'm discussing those which led to very important conceptual developments in the field. And actually, practically all discoveries I'm exposing here got a Nobel Prize eventually. And the same was with discovery of the second neutrino. So discoverers got a Nobel Prize, like eventually Narain got a Nobel Prize. And the second thing, which I'm always repeating, and this is one of the goals of my course, to really understand what is behind these numbers, behind the description of elementary particles we are using, how we got this information. So that's important. Only in this way you can understand what is really the meaning of these things, all the parameters, quantum numbers, and things like that. It's not just some kind of something completely theoretical or something. All these grow from experimental observations. So before discussing discovery of muon neutrino, let me devote a little bit more time on detection techniques. And now I will explain you how a big number of detectors which are operating now work. So this is another way, apart from what I have discussed, to visualize the tracks of the particles. So another way to see the tracks of the particles. And as I said, when particle crosses the medium, it performs ionization. And I have explained already how to visualize this by using, for instance, phase transitions, right? So what we have discussed, or we use photographic emulsions to visualize the tracks of ionized medium. So another way is to enhance ionization. This is what I will discuss now. Enhancement So the idea is very simple. You put electric field. You put strong electric field in your detector. And in strong electric field, suppose this is plus, this is minus, ions produced along the track will move and accelerate. And electrons will go in this direction. And ions go in this one. Electrons accelerate and produce ionization in turn. So you have primary ionization, which is produced by the particle you are studying. So let me denote this. I primary. And there are secondary ionization, which is produced by the particles from the first ionization. When they move, accelerate, and hit other atoms and molecules in the medium. So they produce ionization wider space. So secondary. Ionization. If electric field is not extremely strong, then what happens is that the secondary ionization is proportional to the primary one. There's some coefficient, which is the function of the strength of the field, and multiplied by primary ionization. In fact, this enhancement factor can be quite big, up to 10 to the 5. And of course, if you will further increase the electric field here, it will be discharged. So you can see discharge effect. The detectors which are based on this proportional secondary ionization are called proportional counters or proportional chambers. So, counters and proportional chambers. One of the very important developments in this field, and actually George Sharpak, who developed this, got a Nobel Prize, and a number of discoveries have been done using this technique. These are so-called multi-wire chambers. And among the slides I have sent today, you can find Sharpak with this, with his chamber, and also see the picture how it works. That's inventor is George Sharpak. So what is the idea? The idea is to use planes with wires directed perpendicular. So in this plane, the wires are like this, and that one is like this, and again like this in the third plane. I don't know if it is probably not a good drawing, but you will see much better quality of drawing in the slides. So what is important that you have in one plane the direction of wires this way, and another one like this, and a third one again like this. Now if particle comes through this device, and of course your wires are connected to your electric system, and not only this, they have different charge. So here is plus, this is minus, here is plus. When track of the particle comes, ionizes, and due to electric field, ions start to move. And you collect the signal along these wires. And what is interesting, you will see complicated signal in your electric device, which actually reflects what is the charge connected by different wires. And using this configuration, you can completely reconstruct the track. So you can decode the signal, electric signal you are getting here, and reconstruct what was the trajectory of particle. Okay? Further developments, recent developments of this type of the technique are drift chambers and time projection chambers. And this is TPC, and you can meet a lot of mentioning of this TPC in literature. Actually, these TPC are used not only for accelerator experiments, but such as for dark matter, etc. In many, many circumstances. So what is the idea? You have some volume, and you have electric field again, and then you put here the sensors, which actually connect the signal. So what happens is that when particle crosses your TPC, time projection chamber, it creates ionization. When particles start to move, so for instance, if this is the plus, then electrons are moving in this way. And then you will see projection of your original track onto this plane, right? So because the most of the signal will be along again the projection of your trajectory onto this plane. This is why it's a projection chamber. Now, measuring the time delay between arriving pulses, so measuring time, you can detect Z trajectory, the distance from the point where ionization was produced down to your sensitive plane. So, using time of arrival, you measure the axis Z, and looking at the projection here, you measure X and Y. So suppose this is X and this is Y. So the projection gives you X and Y of the particle trajectory, and time gives you Z. So this is why it is time projection chamber. This is the way how you reconstruct the trajectories of the particles. Actually, these devices people are using, for instance, argon, specific material inside. They give so good resolution tracks that you cannot even imagine. So it's very, very precise image of the tracks in such devices. And I will probably mention one of the major projects in US is DUNE. Maybe I will discuss a little bit more in the last part of the course. And they will use precisely time projection chambers. Of course, there are kind of more sophisticated stuff when you also play with ions, and also sometimes people are using double volume time projection chambers. But the idea is this. So you are measuring secondary ionization. In this plane, you measure this projection of your track on axis X and Y, and by time delay, here and here, and then along this projection, you measure the time on axis Z. This is principle of work of proportional detectors, which are using this regime when secondary ionization is proportional to the primary one. But there are detectors which actually use very high electric field and working in the regime of discharge. So let me say a little bit more. So now we are discussing techniques when the strength of the field is very high. The the early devices of this type are so-called Geiger counters. The electric field is very strong, so the particle crossing this counter produces discharge. And of course it's difficult to measure any characteristic of particle when you have just a detector and you have discharge. And the discharge essentially, the number of, the current will essentially not depend on what is primary energy of your particle. But this is very efficient counter which tells you that some particle comes to your detector. Remember we discussed that in the early discoveries, people just accidentally look at the detectors and saw sometimes the tracks. Nowadays you are surrounding your useful detector by this type of the Geiger counters, and so they will tell you with very high efficiency that something entered your detector. Okay? This is in a sense, active protection of your detector. Suppose you want to search for dark matter or some very rare events in your volume, and you want to reduce background. So you put this anti-counter system which tells you that some particles are entering, and then you exclude events which are then in correlation with outer counters. Now, more sophisticated thing, and that's what has been used in discovery of muon neutrino, is the following. Still, you can use these discharges to see the tracks. Suppose you have, again, trajectory, primary ionization, and the field. But you turn the field for short period of time. So what happens is the following. Particles start to accelerate and produce secondary ionization, and essentially discharges started. But when you switch off electric field, then discharges stop to develop. And what you will see, and you can observe just the beginning of these discharges, of avalanches of particles. So what happens is you have, for instance, electrons. Electrons are accelerated, they knock out another electrons, emit gammas, and essentially if gammas which are produced in this process can further ionize, then you will have complete discharge, uncontrolled, because your gammas can propagate long distances. But again, if you switch your electric field for a short period of time, precisely when your particle came, and you put some Geiger counters outside, something which actually tells you when you should switch on your high electricity, then you will see the beginning of discharges or avalanches. And you can see this by eye, and I will show you, in some of the slides you will see that these avalanches of this size, it's not just a joke, you see these sparks along the trajectory of the particle. So, and again, as in the first detectors, you do a snapshot, and you see trajectory. And now let me go to this, first maybe questions. Let me stop. Maybe I should put the names of devices which are using. So that's the principle of work of spark chambers. Or streamer chambers also. And muon neutrinos have been discovered using spark chamber. Actually, in one of these slides, you will see that these chambers of this size of human being, and the snapshot was done when one of the guys who actually discovered muon neutrino was staying, and behind him you see this sparking track. Okay? So now muon neutrino, discovery of muon neutrino. This discovery has a long story actually. And to some extent it was not accidental. Remember, we discussed the processes like pion decay, and pion go to mu and neutrino, and also decay of muons into nu, e, and another nu. One of the important observations that actually Bruno Pontecorvo again contributed to this was that, first of all, muon is not Yukawa particle. It's something analogy of electron, but with bigger mass. And then it was an idea that probably this muon should be accompanied by its own neutrino. So that, for instance, in this process, neutrino differs from neutrino which appears in beta decay. Remember, in beta decay, that was not ambiguity. You have N go to proton, you have E minus, and you have neutrino. So that's something, neutrino, which is associated with electrons. Here is neutrino which is associated with muon. Here is a more complicated thing. And what we used before is we are saying, okay, maybe this is the same pair which appears in beta decay, and therefore this neutrino is different. So let me put it by plus, this mu plus, then let us denote this muon neutrino. Here we put electron neutrino. Here it is, if mu plus, then E plus, then it is electron neutrino, and muon antineutrino. So I put already this indices before, but that was established later. After all, it is in 1962, when we really concluded that we should ascribe different indices to neutrinos associated with electrons and with muons. So the idea, and Pontecorvo liked this very much and promoted that electron has electron neutrino and muon has its own muon neutrino. And you see what is interesting, that this doublet structure, which we know in the standard model, appears here. So it looks like particles interact in pairs. And they form currents, and the current is formed by electron neutrino and electron, muon neutrino and muon, and not in different way. And already this shows that there is kind of doublet, let me repeat, structure of the theory behind this. So the main question, and you still need to prove this, if electron neutrino is the same as muon neutrino or not. So that was the main question. One of the processes which actually testified that these neutrinos, it seems, are different was the following. That was the absence of decay of muon into electron and gamma. So there's no neutrino here, right? So, but absence of this decay, and it was not observed. It is not observed even now. And there are new experiments which will search for, continue to search for this decay. So for time being, this doesn't exist. But the absence of this decay testified for difference of nu mu and nu e. How one can see this? So we have muon decay, which is transition of muon into nu mu, nu e, and electron. So we know that this type of the interaction exists, right? So we know this decay, and I just put here nu mu and nu e, so these indices. But it's still open question if they are the same or not. Agree? Now, if you have such a process, and if nu e equals nu mu, then you can close this, because this is the same particle. So you have muon, and you have production of muon neutrino, and it coincides with electron neutrino, and therefore you may have such a connection. Now, you of course haven't yet studied these Feynman techniques, but the idea is the following. So if they are the same, then you may have the transition of muon neutrino to electron, so muon to electron, with this kind of the loop. But the physics idea is the following. So muon emits a muon neutrino, and it coincides with electron neutrino, and therefore you can have such a process. Of course, kinematically, this process is forbidden. You cannot satisfy energy momentum conservation if you have just muon, which is transformed to electron. However, electron or muon can emit in addition photon. And therefore your process becomes like this. And this is kinematically allowed. So, bottom line, if nu e is the same as nu mu, then you expect to see, and you should see, this type of the transition. Muon decay into electron and gamma. Now, people made computations. Actually, at that time it was not so trivial, because you have this type of the loop, and when you do computations, and you will see this later, it is divergent diagram. You need to make some cutoff of your divergent integrals. But anyway, you can estimate taking, say, the smallest possible cutoff, which actually doesn't produce new physics for you, because usually cutoff is related to existence of some new particles. So there were some estimations, not exact computations, but estimations of probability of this process. And it was concluded that in fact experimentalists already should see this type of the decays in the early days, in the 50s. And in fact, the Pontecoro was the first who actually made the search for this process, and he hasn't found it. So nowadays, these searches are continuing. Conclusion is, of course, that that testifies that probably nu e is not equal. So the conclusion from this negative result is that nu e is not nu mu, or not completely coinciding. So that is conclusion. And what is present day situation, the best bound is obtained by MEG experiment in Switzerland. So now there's another phase of this experiment, and branching ratio, let me write and then I will explain what is this, which is ratio of gamma, decay rate of muon into E and gamma, small photon, over normal mode, mu go to E and 2 neutrino. This branching ratio should be smaller than 4.2 10 to the minus 13, 1/3. And soon that will be improved up to 4, 10 to the minus 14. by 1 order of magnitude at least. So, the meaning is that if this decay exists, it should be certain orders of magnitude smaller than the main mode of the decay. This is extremely important process. It's not accident that MEC2 now is working and they will produce new results. Is that in this way we are looking new physics. And why we are doing this? Let me say, I'm not sure that you will appreciate completely this. Now we know what are neutrino masses. And this process, in fact, should exist. And it should be proportional to neutrino masses. So this type of the transition should exist still. But neutrino masses are so small that the branching ratio is 10 to the minus 54 or something like this. So in the standard situation, as we understand now, this is absolutely negligible. However, if there's some new physics and some new particles are somehow involved, and this is the process with lepton number violation, then this branching ratio can be at the level of experimental bounds. And this process is extremely important to search for new physics at high energies. And you will see that that kind of the process restricts a lot of things, put bounds on many developments and many models which people actually invented. Let me say maybe that MEC stands for mu to E gamma precisely. This is mu to E electron and this gamma. I have actually a slide with this experiment. Now that was in early days some indication that muon and electron neutrino do not coincide. Decisive check of this idea, and for this check people got a Nobel Prize, was the following. The idea, now experiment. Specifically designed to check that nu mu is not equal to nu E. So the idea belongs to Pontecorvo. And what he was saying that, suppose we have beam of muon neutrino produced by pion decay. So remember we have this pion decay into muon and therefore we should assign here muon neutrino. Remember also that what we have established that this decay is dominant and decay with electron, this is also existing, however it's much stronger suppressed than this. And so pion is very clean source of muon neutrino, muons and muon neutrinos therefore. So the idea was to have muon neutrino and to see how these muon neutrinos scatter on nucleons, on matter. Say, nu mu interacts with N and it is transformed to proton plus muon. This is analogy to inverse beta decay, if you want. But if muon neutrino coincides with electron neutrinos, then you expect to have also transition to proton and electron. Okay? So if nu mu equals nu E, then you expect also this transition. And in the case of coincidence, they should be of the same rate. Of course, one needs to take into account that here is muon, which is a bit heavier than electron, right? But apart from these trivial kinematic factors, you expect that the number of these events equals to number of these events, and mu should be n equal n equal. If you have this incidence. Okay? Question? Now, the experiment has been performed already in the beginning of 60s, and it was used technique invented by Melvin Schwartz to create neutrino beams. And still we are using this technique. So how one can create neutrino beams from your neutrino beam? First, you accelerate protons. So that's from accelerator, nice acceleration. Then it hits material and produces pions among other particles. So proton is strongly interacting particle, and interacting with nuclei in the target, it produces pions copiously, and other particles are of smaller quantity. So it produces pi plus and pi minus, a little bit more pi plus. Then this flux of secondary pions enter focusing system. The system of magnets. Nowadays we are using quite sophisticated systems of magnets which do the following, or there's another name for this, horns. Horns. Maybe one or few horns. Essentially these are magnets. Which do the following. They collect pions and put their trajectory focus along the certain line, one thing, and the second they select among pi plus and pi minus. So using certain magnetic field, you can put out, say, pi minus, and so mostly you will have beam of pi plus. Then this focused beam of pions enters decay tunnel where you have decays of pion to muon and muon neutrino. So this is decay tunnel. It can be of the length of say, it depends on the energy of neutrinos and the energy of protons. It can be, say, 10 meters, and nowadays decay tunnels for high energies are of the size of 1 kilometer. So again, depends on the energy of pions which are decaying, right? And if you have higher energies, of course, the length of decay becomes bigger and bigger. Then, experimentalists put here absorption systems of shielding. An idea is to absorb all the particles but neutrinos. So sometimes it is iron plates, and then a large amount of soil. So usually you have one hole in which you are producing pions which then decay, and somewhere in remote space you have another hole in which you put the detector. So, detector. So you have neutrinos which can easily pass through, And then we'll look for interactions of these neutrinos in the detector. And as we discussed here, interacting with neutrons or nuclei, it can produce muon or electron. Right? So you have some recoil here. And then what you are doing, you are looking for production of muons and electrons in your detector. And in this first experiment, spark chambers were used. And in one of the slides you will see precisely the trap of muon produced by muon neutrinos in this spark chamber. By the way, the energies of neutrinos in this experiment were of the order of 1 GeV. So the experiment has been performed by Jacques Steinberger, Melvin Schwartz, and Leon Lederman, first in Brookhaven in 1961, and next year, 62, at CERN in Geneva. So the result of the experiment, it has precisely this setup, this configuration, was the following. During 8 months, 56 muon events have been observed. And no excess of E events over background. So, of course you have some background, gain electrons which are from the crust, from cosmic rays, from everywhere. And we always need to see if you have a signal or it is just background. So background has been estimated, computed, or even measured, because you can have measurements without accelerator beam. And you see what is the number of electrons appear, or what is the number of muons appear in your detector. And then when you are doing already your useful experiment, you subtract the background. And so this is the result. And the conclusion is that muon neutrino is not electron neutrino. Or, more scientifically, you can say that they are not overlapping completely, because you have state of muon neutrino, you have state of electron neutrino, and you can actually estimate what is possible overlap of these two. So compute this matrix element. So muon neutrino and electron neutrino may be different, but not completely different. They may still have some common part or piece in their wave functions, and therefore what you are doing, usually you are computing this matrix element, moduli square, and from these observations it follows that this is smaller than 0.1, including statistical error, background things and so on. So the conclusion is that even if this new E and new mu somehow are not completely different, this kind of common part is smaller than 10%. I think I stop this, and tomorrow I will first make conclusions from this discovery.